Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome back. So, in the last few classes we derived the mass conservation equation, momentum conservation equations and the energy conservation. And we found a common form or common terms in all of the equations. We had the term which was depending on the temperature, which which represented how the quantity changing with time, or the rate of change of let us say mass, momentum or the energy. Then we had the advection term, where how this the same variable or quantity is changing in space, basically how they are getting transported from one location to another location. So, it does not represent any change in total, but basically it is a transportation from one place to another place. Okay. And then we had the stress term, the forces, due to the viscous forces. You can have the body force or a magnetic force, or whatever term forces that you want to consider, maybe electric force, electromagnetic force. And in the stresses we also had the pressure term. We derived the constitutive relation for the stress for a Newtonian fluid. So, now what we will do, we will look at all these equations in holistic form and see how we can basically represent all these different equations in a similar manner. So, let us look at the equations that we have derived. Before going there, note that from now onwards I will be discussing about the compressible flows only. I may make some comment about the incompressible flow as and when it is necessary, but this course is particularly about doing CFD for compressible flows. So, that will be our focus. So, let us look at the compressible flow equations as we have derived in the last few classes. So, we have this mass conservation equation here, then we have this momentum conservation equation here, and the lastly we have this energy conservation. So, all three conservation laws we have written. We have the pressure gradient term. I have removed the body force here. You can add that if you want. That will not change the basically representation of the equations. So, here the stress term for a Newtonian fluid will be like this. We have assumed the Stokes hypothesis, and the energy we are considering the total energy equation. So, it has got both internal energy as well as the kinetic energy, and for a calorically perfect gas we can write it like this, and H is basically enthalpy. You can also write in terms of E also, and this is the conduction term Qj. So, note that in this entire things the variables are only rho, u, let us write ui, where u will be u v w, I equal to 1 to 3, then p and t. So, 1 plus 3 plus 4, 3 plus 1 4 plus, so this is one variable, 3 variable, 1 variable, 1 variable. So, total 6 variables, right, and we have only the 5 equations, right. So, then we need another equation which is the equation of state. So, which relates the pressure to the density and the temperature. So, that is the equation of state. Other thing is that we have the viscosity, and because the temperature is changing, so your viscosity need not remain constant, in fact, it will change, and you have several laws which basically tells how the viscosity is changing. Okay, this is not necessary for the incompressible flow because the temperature is not changing. For the compressible flow, the variation of viscosity with temperature need to be considered, and this is one law that this is the Sutherland's law in the power law form. Okay. So, that shows that mu basically varies around T to the power half, okay, and in the more accurate form mu is equal to C 1 to the power T 1 to the power 3 by 2 and T plus S. Okay. So, T plus S mu, you can write it here. So, where these are the coefficient which have been determined by basically measuring the viscosity at different temperature, fitting the line, fitting the curve, and then finding these different coefficients, right. So, even the viscosity can be determined if you know the temperature, right. So, this completes. So, now only thing that we need is a proper numerical scheme and a grid, right, because we have the desired number of equations and desired number of basically relations that we need. So, if you want to write this in the matrix form, so what we can do is we can take all this t term, d by dt term together plus d by dx term together, okay, and plus d by dy term together, and so on and so forth, right. So, from the tensor form I will now write it in terms of the matrix form, right. So, in the matrix form, let us say if I am writing for 1D flow. Okay. So, what is the mass conservation? We have only one direction x, okay, and only one velocity which is u. So, we have just one momentum equation, okay, and one mass and one energy, right, and then of course, with the perfect gas equation, right. So, the mass conservation equation will be del rho by del t plus del rho u by del x equal to 0, right. This is mass, momentum will be del rho u by del t plus del by del x rho u square is equal to minus del p by del x and plus the deviative term. So, del by del x sigma x x, right, and similarly the energy term will be del rho e by del t, where E contains both the kinetic energy and the internal energy term, plus del by del x, okay, rho E u and equal to minus del p u by del x, okay, and plus del by del x, and you have sigma x x u, right, and then there will be thermal conductivity term which is basically del q x by del x, right. So, we will collect all the d by dt terms here. So, that will give you this expression, okay. So, now it is a vector, okay, rho, rho u and rho e, these are my conserved variables, okay. Then we collect all the del by del x terms, okay, even the dp by dx and del pu by del x, okay. So, this will give you the second term, okay. So, this is your inviscid term, okay. So, this is your temporal term, this is your inviscid flux, and this is your, you can collect the viscous terms together, okay. So, what are the viscous terms here? This term, okay, this will depends on viscosity, this term, and also you have this the thermal conductivity term. So, this all can come together here, and this is your viscous flux. So, why I have written in this form is because now let us say if you want to solve, let us say only for the inviscid flux. So, you can write this entire thing as let us say d by dt q plus d by dx, okay, and you can have, you can let us call it r, whatever it is, equal to 0, right. You can just solve it in this manner, okay, where q is equal to rho, rho u, rho e, and then r will have all the terms that we have here, the inviscid part and viscous part. Further, let us say if you want to solve for a Euler flow, that means the flow is inviscid, you can just ignore this part and you can just solve these two equations. Okay. Of course, it has to be complemented with your p equal to rho r t, okay, that has to be there regardless of whether flow is 1D, 2D or 3D, and your viscosity should depend on the temperature, and you can use the Sutherland's law for that. Okay. Even your stress terms become simpler in for 1D flow, which is just nothing but 4 by 3 del u by del x, because there is no del u by del y terms, there is no C stress terms in the 1D flow. Okay. And q x using the Fourier's law becomes minus k dt by dx. Okay. If you go to the 2D flow, you can just expand it. Okay. Now, instead of one direction, you have two direction x and y, and similarly you have two velocity v and u and v, right. So, the dy dt term will have this rho, rho u, rho v and rho e, right. And then you will have fluxes. Okay. You can have the inviscid fluxes, which is shown here. It is just the expansion of the 1D equation, or sorry, the 2D equations from the tensor form to the matrix form, right. And your G I will become the inviscid flux in the y direction. So, this is nothing but del by del y term, this is del by del x term, and this is del by del t term, right. And similarly, you can have the viscous fluxes also, which can be written like this. Okay. So, you can see you have the shear stresses also here, okay, but you have only two directions. So, you do not have the sigma x z or sigma y z and so on and so forth, or sigma z z. Okay. So, you can solve this easily, and so these are your final expressions, and you can please go back and write in the 3D equations in the matrix form for the computational flow. You will have some additional terms. It will only make it little bit more involved, but you can just express this h sigma I j q j and so on and so forth, and you will be able to write in terms of complete in terms of your conjugate variables, okay, or primitive variables, and this is the Sutherland's law. Okay. So, with that we will stop. Okay. In the next class we will start the non-dimensionalization of the schemes. That means that right now we have the equations which depends your actual flow values, whether it is velocity or your viscosity or your stress terms, right. So, what we want to do is that we know there are some numbers, some non-dimensional numbers which basically dictates the dynamics of the flow. So, we have read about the Reynolds number and Mach number and so on and so forth. So, can we write these expressions in terms of those numbers, right. If you could do that, okay, we can basically this non-dimensionalize the entire equation, and once we know the number, we can basically find out the desired values that you want, let us say the drag or the lift or any force that you like, right. So, it is good to solve in the non-dimensional form for some flows. Okay. So, we will be discussing about the non-dimensionalization in the next class. Thank you very much.